is how water flows through clean drains. But over time, this gunky buildup slows drains down, and buildup this tough needs special treatment.
Clogged drains too have something to do with today's lesson on acids and bases. Checking the internet, you can find out things such as using vinegar and baking soda to unclog your drain, or even the product Drano. And that particular substance uses a very concentrated crystals of sodium hydroxide and aluminum to unclog the drain. Well, let's take a further look at the strength of acids and bases. First off, we'll take a look at what's called a strong acid. You can recognize a strong acid because it dissociates or breaks apart 100%. Here in my example over here on the left, you can see the addition of 5 molecules of a strong acid. They completely dissociate or break apart, and this can be represented by the equations down below. The first equation is called a dissociation equation, where the substance, as mentioned, breaks apart into its ions. The lower equation shows an ionization reaction, the substance ionizing with the water. Both are considered to be the same. However, in the case of a strong acid, you end up with virtually none of the reactant left. It's completely gone. And in this case, we can assume that the concentration of the acid particle is equal to the initial concentration of my acid. Again, if we refer to the diagram, I put 5 particles of acid in and ended up with 5 hydrogen ions. The equilibrium constant for both of these reactions is very, very large, again, suggesting lots of product and very little reactant left over. Now, our strong acid list includes things like hydrochloric, nitric acid, and sulfuric acid. But a word of caution about sulfuric acid, although it's diproduct and has 2 protons, it's only the first hydrogen that breaks off very readily. The second hydrogen is a little bit more difficult to remove. A couple features of strong acids. We'll take a look at conductivity for one. These substances are excellent conductors of electricity. The presence of the ions allows electrons to move freely through the solution, and the light that we're using to test here would give a very bright indication. They have relatively low pH values, 1 or 2 perhaps, and they react more quickly than the comparable acids that are in the weak category. So for instance, if you were to mix a metal with a hydrochloric acid, you would see a quick evolution of bubbles if you had a strong acid. Now, weak acids, on the other hand, they don't dissociate to the same extent. So if I take my 5 particles and place them into the liquid down below water, I may only find a small percentage of them that actually break apart or ionize. That's why we use an equilibrium arrow here, indicating that we have sort of an abundance of both reactant and product present. In this case, the concentration of the hydrogen ion is much, much less than the original concentration of the acid, and the equilibrium constants for these reactions are very small, often in the order of 10 to the minus 4 or smaller. Weak acids include things like vinegar, hydrofluoric acid, and carbonic acid, which we often find in pop. These substances, when you check their conductivities, are extremely poor conductors due to the relatively few ions you have present to carry charge. Their pH values tend to be somewhat elevated compared to their strong acid counterparts, meaning their pH values could be 3 or 4 range. These also react more slowly than their strong acid counterparts. So again, mixing them hydrofluoric acid with magnesium, I would get a much slower evolution of bubbles. But it is interesting to note that I will eventually end up with the same amount of gas being produced, but it will just take a longer period of time, provided I started with a solution of similar concentration and the same amount of magnesium. One of the interesting points about these 2 substances is how do they behave when they're being neutralized? So in this case, I'm going to use sodium hydroxide, and I'm going to represent the hydroxide ion by the presence of these small triangles. On the left-hand side, I have my strong acid. So the reaction we're going to look for here is a neutralization reaction, the acid particle mixing with the base particle to produce water. In the case of my strong acid, it's completely dissociated, so I have 5 hydrogen ions present, and then by means of titration, I'll need 5 of my base particles to essentially neutralize it. Now, let's look at the situation in a weak acid. I have hydrofluoric over here on the right-hand side. Only one of the molecules dissociated that was placed in. So I'll begin by adding my base. The hydroxide then neutralizes that hydrogen ion. Now at this point you might think the reaction's over, but you need to consider Le Chatelier's principle. The removal of that hydrogen ion will shift the equilibrium so it breaks apart and produces more. That will then require another base particle to do the neutralization, which again will shift the equilibrium, forcing another particle to dissociate. So as you can see, what at first glance might have looked like a situation where I wouldn't need as much will essentially need the same amount, all because of Le Chatelier's principle. In both cases, I'm going to need the same volume of base to neutralize equimolar concentrations. So that's an important feature, is that both strong and weak, there's no way you can tell them apart from neutralizing them. But there is something about their energies that you can use. Strong acids will have a slightly higher enthalpy change. The reason for that comes from our knowledge of bonds breaking and bonds forming. In a neutralization reaction, we're forming bonds. The hydrogen and the hydroxide join together and release energy, usually in the order of about minus 57 kilojoules. In the case of a weak acid, some of that energy is needed to break apart the bond between the hydrogen and the fluorine. So in this case, you get a slightly less exothermic reaction because you need to use some energy to break apart that bond. Strong and weak bases follow similar arguments. Strong bases dissociate completely, whereas weak bases don't. They have Ka values that are very large for my strong bases and very small for my weak bases. They're not very good conductors, weak bases, but much better conductors as strong bases. pH values, again, tend to be very high for my strong bases, but tend to be somewhat closer to 7 for my weak bases. And again, the arguments around conductivity. The presence of lots of ions in my strong bases make them excellent conductors, whereas weak bases have very few ions and as a result are very poor conductors. Most metal hydroxides constitute the strong base category, whereas ammonia and many amines constitute the weak bases. So I hope that this has helped you out a little bit with your understanding of acids and bases. And remember that if you like these programs, please give me the thumbs up. And if you can spend the time, a few comments would be helpful. Thanks a lot.